Hello and warm welcome to everyone to the 23rd lecture of the course on financial econometrics. Today basically we will talk about very core concept of the time series analysis, that is about the concept of stationarity. So what is the concept of stationarity? Before that, let's us try to understand in the more detailed way what we mean by the stochastic process, though briefly we have discussed in previous lectures. So, the stochastic process, or what we call in general a data generating process, is basically can be understood this way. Let us say yt is the data generating process. Then here we are assuming that it has been very well aptly has been defined by Harvey, that is stochastic process may be defined as a collection of random variables which are ordered in time. So it's a collection of random variables ordered in a time. So basically what we have an observation, for example, a series of GDP, it could be a stochastic process, or a series of the stock prices, it is a stochastic process. That is a very narrow approach to define the stochastic process. What we mean by the stochastic process, that can be captured by this particular image. So here basically let us say this YTG is stochastic process, and then it has been started from here T to so we can very well capture the concept of the stochastic process. We can understand the concept of a stochastic process more easily using this particular image. So here let us say this YT is an stochastic process. Then Y1T here basically one of the possibility of this YT to have the observation is, let us say, Y1T. So it varies over the period of time. So as time passes, this could have been one of the observations. Second possibility of the same series could have been this different random variables ordered in this over the period of time. So basically stochastic process, what we mean, let us say the stock prices. So stock prices have infinite possibilities to hack the observations. It could have been followed this particular path, or it could have been followed this path. So there is the n number of possibilities to have. Then out of this one basically we see and we observe. So what we mean the stochastic process, basically you can see here that for example you can consider a weather station. So the different weather stations captures this data at the different time period. So this is the over the period, and these are the different weather stations. So that's the basically the concept of data generating process here. Then what is the time series? So basically this time series is the one realization, as Kiskan and Walters has defined. A time series is considered as one realization of the underlying stochastic process. So basically out of that n number of possibilities, we observe one of the variables, one of the realizations we have, one of the path we have. So this is the known as the time series. So there was n number of possibilities we have for the random variables ordered in time. Out of that one we realize that is known as the time series. So before understanding the concept of stationarity, so let us understand the concept of ergodicity. Because this is the ergodicity for which the development of stationarity has happened. So let us say this is the stochastic process we have. Now we can take average of this in the two different way. Either we can take average for a particular observation over the year. So in that case, what we have, we may have this particular average, that average of this y, one of the realization over the period of time, and let us say time here is the infinity. So we can say limit of this average of t reaches towards the mean of this y process. Or we can take the average of this stochastic process at a particular point of time. So, we can have this average at a particular point of time for all those possible realizations. So, here for example, we can take the average of the temperatures captured by all the machines weather stations in a particular country, rather than taking average of the temperature of one machine over the period of time. This particular average, this method is known as the ensemble average. So, this could be like this, that here n from n, so this is the basically all those possible realized observations, we are taking average of that. So, this is, so there is the two possibilities for the stochastic process we can take. So, what is the concept of ergodicity? Ergodicity is a very simple concept. What it says that when the average ensemble average and average over the period of time for a particular observation, realized observations across the time is same, then we will call that stochastic process has the property of ergodicity. So, that is what we mean by the concept of ergodicity. So, this explanation we can convert into the mathematical notation like this, that basically ergodicity means that the sample moments which are calculated on the basis of a time series with a finite number of observations. So, basically time series means one of the possible realizations we have, we are able to calculate. So, using one time series observation converges for t tends to infinity against the corresponding moments of population. Here the population is that stochastic process. So, if both are becoming same, then we can say this is the ergodic. So, here we have stochastic process yt is said to be mean ergodic if the limit of the expectation of yt minus mu t, here mu t is the mean of the stochastic process, is equal to 0, then we will say it is a mean ergodic process. Similarly, we can say it is a variance ergodic if as t tends to infinity, the limit of the variance of this yt and the population, then the limit of the difference of the variance of this time series and the population becomes equal to 0. So, if that is the case, then we say that particular series is having the ergodicity property. So, now let us understand how we characterize or specify a particular distribution of the data. So, any series, let us say stochastic, any series we have yt of the dimension t can be completely described, it can be characterized, it can be identified by a t dimensional distribution, isn't it? The t different dimensions we have, then every dimension's measurement, every dimension specificity we have to certain to say that yes, this particular distribution is this defined by these are the different dimensional characteristics. So, to in actual sense, any stochastic process yt can be identifiable only when we have all the dimensions captured. However, that is not feasible because we know that when we draw the more than 3D figures, it becomes difficult to realize that. So, due to the practical feasibility, however, we are concerned only for the two movements, that is the mean and variance. So, mean is expectation of y I is equal to mu t and average value of yt taken over all possible realization at time t. Similarly, variance is nothing, it is calculated as expectation of yt minus mu t to the whole square. So, we calculate the variance as yt minus mu t expectation of yt minus mu t whole square. So, this is the variance and the covariance we can calculate using this expectation of multiplication of yt minus mu t into ys minus mu s. So, these are basically these three parameters, three we take to identify the characteristics or distribution, to specify the distribution of a particular stochastic process. However, this is possible only when we have several realizations available. Then only can be estimated using this particular example, can be calculated. However, the several realizations are available of the stochastic process, then only we can calculate the mean or variance or covariance. For example, we can calculate the mean like this, where yt, j is the jth observation of on yt and m is the number of realization. So, the every realization we can calculate, but we know that we have only one realization. So, how we then move ahead? So, for that property basically we need the concept of stationarity, or this practical difficulty leads us to the idea of stationarity. So, what we mean by the stationarity? Basically, a stochastic process has to be stationary to be ergodic. You know why ergodic? When the mean across the different system at the same time, or the average of one realization over the period of time, if both are the same, then only we say that system is ergodic. However, what we are concerned about in case of stationarity, we are concerned about the moments at a particular point of time. So, if the series is stationary, then only it can have the property of ergodicity. So, what we mean by the basically is stationary, that we need the consistent distribution over the period of time. If the distribution of the particular time series is same at the different period of time, then that's what basically we are concerned here. So, the distribution depends only on the gap between times, not on the location of time. So, to understand that, let us say we have this particular image. So, what we are basically concerned here, let us say we have the two time width. So, here what we have, this time width is different than this time width. So, if this is the situation, then obviously average, mean, variance of this particular observations will be surely different these observations. However, if the time width is same, then what we stationarity means that the distributional property of this observation should be same of this observation. So, basically if the time width, time gap is the same, then the distribution of those observations should also be same. If this exists, then we say that there is the strong or strict stationarity properties we have. That means all the distributional characteristics should be same if the time gap or the width of the time are the same. However, that is very difficult in the real world to realize. So, we have a little different concept, what we know as the weak stationarity, where basically we are not concerned about all the characteristics of a distribution. We are concerned only with mean, variance and covariance. That is, any series, this particular will say that this series is weakly stationary if the mean, variance and covariance of this is the same than this. So, in these two cases, since the time width are the same, if the mean, variance and covariance is same, they will say this is the weakly stationary series. So, that means it does not depend what is the point of time, but it depends only what is the time gap we are taking. If this mean, variance and covariance does not depend on the location of time, rather than it depends on what is the time width, then that distribution of that particular series is consistent. That means that series is stationary. So, let us see these conditions in the mathematical notation. So, basically what we are concerned, strict stationarity will prevail only when if the joint distribution function of this stochastic process yt does not change by a shift in the time. So, the probability function of this is same with the probability function of this, despite here the time period has shifted by m. So, here t1 plus m up to tn. Now, this tn is by m. So, if the probability measure for the observations yt at time 1 to n is the same at the time 1 plus m, 2 plus m and n plus m for all the m, then we call that this is the strict stationarity wave. In this case, all the distributional characteristics are time independent. However, that is rarely realized and very difficult to practically assess. So, we use the basically concept of weak stationarity, and most often this will be enough for the distribution for the modeling purpose, for the modeling or the analysis of the data. So, what is the weak stationary or weak? That if a stochastic process say yt satisfies the following three conditions, those conditions are mean stationary if the mean is time independent, that is it is constant across the time, or variance stationary if the variance is also constant for all the time period. Then covariance stationary, that is the covariance between these two observations depends on the time gap, not on the location of time. So, basically this reflects that this covariance depends if it is between 2 to 6, that is the time gap is 4. Now, rather it is 6 or 10 or 8 or 12 time period. So, since the time gap is same, then the covariance is same. If this is the case, then we will say this is the weakly stationary. So, the time gap not on the location of time. So, let us take an example here. So, that means a weakly stationary stochastic process, also known as the covariance stationary process. So, let us take an example of this here. So, let us say a sequence or the series of the uncorrelated random variables with constant mean and variance, say ut. So, there is no autocorrelation. So, the current observation does not depend on the previous observation and it has a constant mean. So, let us say 0, variance is sigma square. In that case, what we have this situation. The stochastic process of this ut is basically called pure random or the white noise process, and it has following property. What property we have? Aspect function of ut is 0, and obviously if it is constant or 0, it will be same for the all the time periods, and the variance of ut is sigma square for all t, and covariance is always equal to 0 because there is no correlation between this particular series. This is uncorrelated, and this is the example of stationarity process because the mean is constant, mean does not depend on the time, variance does not depend on the time, and the covariance also does not depend on the time. So, we can have example this is the example of white noise process. If we plot that, the data will look like this. Then let us take an example of non-stochastic process. Let us say we define an stochastic process like this: yt is equal to u1 plus yt minus 1 plus ut. That is, for the first observation where time period is 1, we have this observation. In the next time period, what we have? Yt minus 1 plus ut. So, that means previous yt plus ut. In that case, what we will have? Where it is pure random. This particular formation is known as the random walk without the drift. So, here let us find out what are the properties it has. So, this can be represented yt is equal to in form of uj, j is from 1 to t. So, let us say what are the properties we have. So, do you think you will be able to look, say, any real world example which follows this kind of path? So, basically I will give you an example. So, have you observed how the drunkard people or the drunken man walks. So if you carefully watch how they walk, basically they follow this particular path. They follow this particular process. So I will show you how we can observe that in a moment. So let us first see what are the properties we have in this case. So first property, that expectation of yt. So expectation of yt, we can write expectation of this whole series, because this yt is represented by this, we can write like this. And we know that from the property of the expectation, this summation will be outside and expectation will go inside. And we know that the ut is the random process. So obviously then expectation of ut is equal to 0. So that's what we have written. This is 0, then summation of all the 0 will be also 0. Now let us say the variance of yt. The variance of yt, we can write the variance of yt like this, then summation of outside, then we can write variance of uj. Again, as we know that this ut follows a white noise process where mean we have 0 and variance is sigma square. So in that case, variance of u will be sigma square. Now here, this is the summation of sigma square from j and here we have this summation of variance square from j1 to t. Let us say for the moment we have only 5 time periods. So in that case, what we have? Sigma square, sigma square, sigma square, sigma square, sigma square. So here we can write 5 times sigma square. That means this 5 is basically what is the value of t. So if it is 3, we can write 3 sigma square. If it is 2, we can write. So in general, we can write t sigma square. So the variance of this series is t sigma square. Now let us say what is the covariance. So covariance here we can calculate using this particular formula. So here we can have expectation of uj and us. So in that case, here if you are writing the expectation of uj and us, then they will minimum here this. So what will be this? Why we will write this? Let us say minimum of t or s. So basically what we have the 2 series here, 1, 2, 3, like that. Let us say u6. Then another series is us. So us could be start with the 2, 3, 4. Let us say this. Or we can write u5. So in this case, if we wanted to make pair, so u1, u2, then we have u1, u3, u1, u4. Similarly, we will have the series like this, u2, 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 u3, like that. So what we have, this we know there is no correlation, so it will be 0. Here it will be also 0 and here it will be also 0. However, u1 to u2, it will be nothing but the variance. So in that case, it will be, the value will be sigma square. So in that case, how many pairs we will have like this? We will have pair like this, and similarly here you have u4, then you have u5, then u6. So u6 don't have pair. So it will depend how much pair we have. It will depend out of ut and s, which one is minimum. Here, because s was the minimum, the value of sigma square will be same as the s. That's why we have written minimum of t or s sigma square. Whichever is minimum, that will come here. If it is s is equal to 4, then we will write 4 sigma square. Then the value of covariance will be 4 sigma square. That means it depends on the time. So now if you observe here, though mean does not depend on the time, however, the variance and covariance of this particular stochastic process do depend on the time. So if the time value is changing, then this will also change, and that means this is not an stationarity data. It does not have the property of stationarity, or we can say it is not an stationary data. Though mean is stationary, but the variance and covariance is non-stationary. So let us say how it look like if we plot this particular data. If we plot that particular data, that's how it looks like. So what we have, we can test this using the graphical method. So let us take the same here. So this is the same time width we have, and here also we have the same time width. So let us compare what is the variance. So you can see the variance of this, and you can see the variance of this. So obviously here we have the larger variance compared to here the smaller variance. So that means as the time is changing, so the time, though the time gap is same, as the time is changing, the variance is changing, and the covariance is also changing. Here you can observe this part, and here the other parts, that covariance also do depends on time. Therefore this particular series is non-stationary. So as we have told, this is the quite similar in the real world to ask the drunken man. So let us say how the drunken man walks. So it takes some step here, then goes up, then coming back, then goes up, then moves right, sometimes moves left. So you will have unpattern. So if you clearly observe, that's how a drunkard walks. So in that case, you cannot have the time independent mean or time independent variance. So this is the one of the example of the non-stationarity data. Now let us say if we have the non-stationary data, for example here you can also observe this is the non-stationary data. Since it is easy to see here, if you take this time width is the same, and here is also time width the same. However, if you try to find out the average of this section of data and average of this section, that is the mean of this section and mean of this section, it will not be same. It will be surely this chunk will have lower mean compared to this particular chunk of data. So that means the mean is itself time dependent. So this data is non-stationary. Now if the data is non-stationary, what should we do? How we can make the non-stationary? If we take the difference of this data, that is if we take delta yt is equal to yt minus, if we take the difference, we will see by taking the difference we have this data. So basically the moment we calculated this difference yt is equal to yt minus 1, that is from the current observations we have deducted the first observation. So that is, let us say here y1 is equal to y2 minus y1, delta y2 is equal to y3 minus y2. So we will get a series, and this series will behave like this. Now if we can observe here this the mean of this section, and with the similarly here mean of this section. So you can observe if the time gap is same, the mean is here is also same of this section and of this section. So that means mean is time independent, and so is the variance and covariance. So by taking the difference of the original series, it turns out to be, it has become the stationary. So if that is the property, we call it difference stationarity series. That by just taking the difference, we will be able to make it stationary. So both the series here I have shown here. So it was earlier non-stationarity. By taking the difference, we have make it stationary. So in that case, what we call, so if the series can be made stationary by taking the, if a non-stationary series can be made stationary by taking the difference, then we call it a different stationary series. Then another way, sometime just by removing the trend, we will be able to make it stationary. If that is the case, we call it trend stationary series. So that means usually there are the two approach we can adopt to make the non-stationary data into stationary, so that we can use in the for the further modeling or for the further analysis. So today we have discussed what we mean by the ergodicity, what we mean by the stationarity, and how we basically measure the stationary, how we assess whether the series is stationary or not. Within the stationarity concept, we have the two concept, that is the strict stationarity and the weak stationarity. In the practical world, usually will be limited ourselves to the weak stationarity concept. So today we will end here, and in the next class we will discuss how we can test the formal, what are the formal tests we have to detect the non-stationarity or the stationarity characteristics of a particular series. Thank you for being with me, and see you in the next class.